and we conducted a study to compare human performance with biological and biological, bio-inspired and non-bio-inspired models. And we wanted to say how all of these compare when they're trying to perceive human body motion. The final applications will be clinical, but this was a proof of concept where we wanted to compare these models with an objective where humans are supposed to be good at, which is gender identification from motion, from skeletal motion. And we wanted to strip it off of any external cues like hair or clothes or body shape, so we just stuck to the skeletal body motions. And the task is non-trivial because it's very confusing about what the gender of these walkers are. So we did the comparison, and the details of this comparison are on my poster there, and the answers to what the genders are of the 4 walkers in the video are also there. But we noticed that if you take bio-inspired systems off the shelf, we didn't add any bells and whistles. It was a simple networks that we took off the shelf and just trained it directly on the sort of training data that we expect would be the closest to humans. And we found out that simple bio-inspired networks outperformed humans in tasks where humans are supposed to be good at for social and reproductive objectives. And it is possible for us to replicate the exact human output. If we take an LSTM network and we train it for animations that last 0.5 seconds and more. More details on the poster. Thank you.
I'm going to say a few controversial words, but never mind. First of all, the problem of selecting features to do pattern recognition. There is no guarantee that those features would strongly be present in unseen data. There's no guarantee. Secondly, the training data that is used to train up classifiers, there can be no guarantee that that training data properly represents unseen data. So there are sources of error here that are quite worrying. Now, I've taken an approach that looks at commonality between reference images and candidate images. The measurements that I'm taking are firstly brightness gradient direction for each pixel, and also the angular relationship between pairs of matching points in the 2 images. That gives us a matching clique between the reference and the candidate, and we've got 100% result on 200 reference images and 200 candidates, 40,000 comparisons, 200 of which are right. Now there's one other thing that I can mention about this, and that is brightness gradient direction. I typed that into Google a few months ago, and up popped a paper by a Russian in 2001. He was looking at cells in a cat's brain, and he discovered that there were cells that were sensitive to brightness gradient direction. That is quite good fun.
I thought this one goes into the junction box of yours because I found your email in my junk box. So, yeah, I'm Wen Shizhuang. I'm a postdoc in University of Southampton. I'm working in a cross-disciplinary project to help ecologists find the leading factors when the speciation happened. So my poster is over there. Apparently, it fails done. So if you're interested in this one, I'm happy to talk and discuss. I'm sorry. You have to prove.
Okay, so this is mine. What we present here is actually
actually it is we do the shadow detection and the shadow removal simultaneously. So as we know, shadow it will provide important information about shape and also give us important information about the light sources. And normally, what we do in computer vision part, it is we treat it as two separate tasks. We can do shadow detection or do shadow removal. But actually, we know that these two tasks are closely related to each other. So here we present a multitask again. So it is we treat that because they have some shared features. Shared feature for these two tasks. So it is we treat them as, so we want to create the two results at the same time. So in order to finish this task, so here it is we proposed, we call it is a cross stitch unit that is can adaptively to shared features, and also for the lost functions, it is we automatically control the distributions of the shadow removal and the shadow detection and the shadow removal, and we get relatively good results. And I'd like to have a discussion if you are interested in this. Thank you.
Hello, I'm Lindsay MacDonald from UCL. This is my colleague Katarina Meyer from Bratislava. This is all about colour. The stimulus that reaches the human eye is a spectrum, a full spectrum, which is a product of each wavelength of the power output from a light source and the reflectance from an object, or a point in the scene. And the eye projects this n-dimensional spectrum into a three-dimensional colour stimulus. These are the three cone responses according to spectral sensitivity. A different observer, like a camera, will also produce a triplet of signals, but with different basis functions. So these will be different triplets of signals corresponding to the same spectrum. So our question was, how well can a neural network establish that correspondence? The way that we approached this was to train a neural network with synthetic spectra, which were realistic. They have the characteristics of real spectra, but generated with a number of basis functions. And we produced 100,000 in each of 8 categories.
Right, and then we tried to fit a deep neural network to establish the correspondence, and we trained, as Lindsay said, we trained on artificial data and tried to test it on actual data. And we established that actually it can be done pretty well, and our mean error was this one, R square was 99%, over 99%, so it's doable, basically.
And the color errors are less than 1, less than a just noticeable perceptible difference. So we're very pleased with this result.
Okay, so we now have the next poster session. We've got 45 minutes to chat and discuss and maybe have some more coffee if you're lucky. And then we reconvene at 3 o'clock.